Nice to have you all here. Let's do our lecture 1.
I just still the reading this week was like the preface, and then the chapter 1, and then section 1 through 3, and then on Thursday we have a reading quiz, and then we have a homework due on Thursday.
Right.
Okay, perfect.
Good question. Any other question? Yeah, and it's deliberate because I wanted to really grasp this first part, this beginning of quantum mechanics. The connection with experiment is usually what many people forget, and they get caught up with the theory and then wonder what it means. It was derived to explain experiments. Does that make sense? That's what we want to do. That's what we want to emphasize. Birth of quantum mechanics. That's why the reading, as you asked, is chapter 1, sections 1 to 3, including preface, so that you really get where we're heading to. And then the quiz is on that. So the material for the quiz, we are going to cover it today. And part of the material for the homework due on Thursday, we are also covering it today. And part of that material is something not new to you because it is statistics. Any other question? All right, so just fun fact. Birth of quantum mechanics, connecting it with something really real, our eyes. It's now been found that what led to postulating quantum mechanics, part of it, photoelectric effect, that in fact, our eyes can detect individual photons. Wow. Oh, yes. That was shown in 2016. Our eyes sensitive enough for individual photons, something that was postulated based on photoelectric effect right there, and the theory worked. In fact, we can detect those things that were supposed to be like hypotheses. Maybe light is coming in as packets of energy, which we can call photons. It's real, super real. And then, guess what this might be? Still an attempt to root it in concrete reality, including technology. This is an electron microscope image of something. Can you guess, please? Because you are wearing the face mask just as I had mine, so now you can guess. Anybody wearing face mask? Just as I had mine right there, can now guess. What is this?
The coronavirus?
Absolutely. Why is it there? Electron microscope. It's what enables us to see it. What's the size of the coronavirus? About 0.1 micrometer, 0.1 micron. Can we see it with light microscope? No. The only thing we can see, size of stuff we can see with light microscope has to be above 0.5 microns. These viruses are less than that. We need what? Electrons. How did we get to electron microscope? Because we understood the quantum theory, we understood that these electrons, they are particles, they are behaving as waves, and then you can use them the way you use light. Light, waves, so you can take pictures, right? Electrons, they're behaving like waves too. You can also use them like waves and take pictures, and their wavelength, the Broglie wavelength, is much smaller than the wavelength of visible light. Therefore, you can see smaller things with it. Cool. Yeah. So quantum mechanics is super cool, born out of the need to explain the way reality works. Stuff about reality we only discovered much later in the 20th century, late 19th century and early 20th century. That is what led to birth of quantum mechanics. So your question was very good. Where are we? What are we doing? So I'd like to show you all. We started out with organization and all that. Today is birth of quantum mechanics. See, the reading is preface and that. And then self-assessment was due because I wanted everybody to do it. And then on Thursday we'll repeat that because we want to be thorough. Based on what I'm going to say today, you're going to read it with new and maybe fresh zeal. You don't know what to look out for. Is that okay? and then you will be fine with the quiz. The quiz will be very simple after all we are doing here. And so, remind us, your question also showed why I'm doing this. Now everybody gets to see. So please go to blue line, and this is where we are. So with 2, that's what is due today already. And then reading assignment right there. Quiz 1 coming on 26, and then homework also. It's just 3 of them, and it's about the statistical interpretation. And week 3 is already there, so no confusion. And chapter 1, sections 4 to 6, and then there will be quiz 2. Is that okay? Any questions so far? All right, so let's go straight into, oh yeah, I have clickers and I have already registered you, so you don't have to bother. And when we are ready, we'll use the clickers, okay? But you may want to take note of your numbers. How many of you are taking other classes, other courses in this class, in this room? Yeah, so you maybe in those other courses, your clicker numbers may be different. So you want to write this down, because I may not show this page every time. I may do it two more times. Okay. So from last time, what is quantum mechanics? It's a theory that explains nice experimental results, a fundamental theory. And what does it do? Yeah, it explains stuff that could not be explained by physics that we had prior to it. Classical physics, classical mechanics in particular, and classical electromagnetism. Do we always understand quantum mechanics? That's a good one to introduce the reading. But based on the reading, what do we get from quantum mechanics? It explains our experiments. We know what it does, but we don't always understand further questions about why of quantum mechanics, about the nature of quantum mechanics. But as far as the results of our experiments are concerned, the theory allows us to make sense of the experiment and to also make predictions. Much like, actually, Newtonian mechanics. We will see that today. So it turns out that when we ask the deeper questions about why, for example, well, what is the wave function? Is the electron waving? When we make measurements, we say that the wave function collapses to that result. Where was the electron before the measurement? You saw such questions in the reading, right? Yeah? And then to show that it is so counterintuitive, the interpretations of quantum mechanics are many. Which interpretations did you find in the reading? Anybody? Anyone from the reading? Yes?
Like, do you mean like where they think the particle was before the...
Exactly. It leads to 3 interpretations, and I just want you to state which one or 2 of those. Yeah.
I don't remember the name, but I know one is like, it's at that same point, and then...
It was always there. That is the realist interpretation. Yeah. So realistic. What we measure is what is real, right? Good point. Thank you. Yes, next, another, yeah.
There was the orthodox position.
Which is different from the realist. The orthodox says, well, our measurement has done something fundamental to the position. It is our measurement that sort of forced it there. Measurement in quantum mechanics is counterintuitive. And that's the orthodox position. It's also the statistical interpretation, and we're going to introduce it today. Isn't that beginning to be a little bit, what is going on? The third one, now that we're at it.
You can never know.
You can never know, the which is like the agnostic.
Okay.
Yeah, don't bother me. And that's because you are kind of prodding. You know, our author, the text author is very good he writes in a conversational way. So it's like, if you insist on the questions, you may get, okay, no answer. And then some people say it more bluntly. Stop asking me what is waving. Just give me the wave function and let's do the calculation and let's make our prediction. But don't ask me the deeper nature of quantum mechanics. And like the author said, if you cannot wait with this introduction and our delving into the statistical interpretation, which is the orthodox or the Copernican interpretation, then you can read the afterword. But of course, I'm more than happy to handle some of the questions as we go along. Just that, as the author said, the questions become easier to handle or more concrete when we actually know what quantum mechanics does. And we're on it. Okay. So, today, birth of quantum mechanics. At least 10 influential figures. May not give the whole history, but at least this is historical. So you will hear us talk about the Born interpretation, which is the statistical interpretation, and it's right there. And most of these guys lived or did their work between 1900, when Planck made that hypothesis, and 1927, when we had concluded with the Schrödinger equation of 1926. So it is largely the physics of the first quarter of the 20th century. And it's still valid. So, just to emphasize, these big names were actually contemporaries, people who worked together. Yeah, and you've seen this in your modern physics. You've seen this picture again and again. How many have seen this picture in your modern? Very good. So let's try to identify some of them. I'll start with Marie Curie, right? Okay, so let's see. Who can we identify just by looking? Einstein, right? Who else can you identify? Yeah, let me leave you with the fun of, if I touch, you can guess. Schrödinger. Yeah, Schrödinger is right there. And next, Dirac, right there. They were contemporaries. And the Schrödinger equation is non-relativistic, but the Dirac equation gives us relativistic quantum mechanics. The emphasis is that they were contemporaries at conferences, and they were dealing with what we're talking about, electrons and photons, the experimental results that could not be explained. So they all knew the big questions of the time, and were dealing with it in their own work. So you can go around and see all of them is right there. So their work led to quantum mechanics. And in some cases, what appears to be its confusing origin, not really confusing, but it's not like Newtonian mechanics where one major figure put together something. In many cases, they were working independently, using different methods, and ended up with the same result, which was kind of cool. For example, Werner Heisenberg did the same thing that Schrödinger did. Schrödinger using differential equations and giving us the differential equation as the Schrödinger equation. Heisenberg using matrices and giving us matrix mechanics, which leads to the same result. And who showed that they were the same result? Dirac. Yeah. So we'll be talking about these various results or various ways of arriving at the same result, leading to different kinds of, if you like, pictures of quantum mechanics. And I like to do a lot on the board. You just saw the Solvay conference of 1927. That Solvay conference continues, and questions abound today. And most of the questions people are concerned about go into areas such as quantum gravity. Yeah, quantum electrodynamics is so accurate, so nicely done, but how do you take into consideration quantum effect with gravitational forces? That's hard. There's a lot of work still to be done, and practical results or practical expectations of technology push it nicely. So people want quantum computers. But people also want better forms of energy, green energy, and all that. That's why we are going into learning from even other things that exist. Plants, photosynthesis, for example, is a quantum phenomenon and super efficient in converting light energy to chemical energy compared to our own method of converting solar energy to useful energy, electrical for us. Maybe we can learn from the plants. Yeah? Objects are already engaging in a lot of cool quantum mechanics. So quantum mechanics is so high. So what we're going to do shortly is to use equations. I started this last time. We did 5 equations. I'm going to do 5 more to use equations to go through the birth of quantum mechanics from experiments to wave function up to statistical interpretation today. So if you don't mind, James, you can please. So we do it on the board as quickly as we can so that maybe the first 30 minutes of every lecture will be like this. Introduction, stuff on the board, and then we do some exercises together, including going into details on the slides. Is that okay? All right. Let's see if we have the picture of the board clearly. And make it faster. Yes, and I can indicate where the camera is. So right here. And the other part of the camera. Yes. How many do I need? I think I could do 3 today. Yes, so that's, we can recall, so birth of Creighton today. And we want to emphasize the experimental results, yeah? That could only be explained using quantization, therefore leading to quantum mechanics. So you recall, we said energy had to be quantized, energy of absorbers of electromagnetic radiation. So you could call it oscillating, if you like, had to be quantized using Planck's constant. Yeah. What else? So that's Planck. What else did we say? So experimental result, black body radiation, for example. If you heat up a body, warm up a body, yeah, it's going to emit radiation. In what form? It has to be quantized. If not, you end with ultraviolet catastrophe. Planck made that hypothesis and explained experimental result. Secondly, we mentioned what? Sorry? Yes.
Energy of a photon is
So, exactly, energy of a photon itself, not just absorbers of photons or emitters of radiation, but the photon itself, and that was Einstein. Thank you. So H bar omega, that was Einstein. What else? Number 3 that we mentioned last time. Something else is quantized. Yes, please.
Angular momentum.
Yes, angular momentum is quantized. So N H bar, and this was Niels Bohr, right? The Bohr model. This was a way of explaining. So it led to orbitals, orbits. Yeah? Number 4. What else is quantized? Experimental results. So atomic spectra could be explained, or so atomic spectra. What else, please? We did 5 of them.
Linear momentum.
Okay, so linear momentum, P equals H bar K, where K is the wave number. What does this say experimentally? What was going on? De Broglie hypothesis that photons themselves must also be quantized, yeah, with momentum, with quantized momentum. So Millikan showed that, Compton, photons are quantized, and they come with quantized momenta, which Compton proved experimentally. That inspired De Broglie to say maybe matter also, material stuff like electrons also have wavelength and could be quantized, wave-particle duality. So, De Broglie. That means electrons have wavelengths, and if you don't believe it, well, how did we know the size of the coronavirus? It's an electron microscope, thanks to the wavelength of the electron behaving like wave, yeah. So we did this, and it led us to number 5, the birth of quantum mechanics, to put this together, which was what? The Schrödinger equation. Okay. So let's say time-dependent Schrödinger equation and time-independent Schrödinger equation. And we can write that on this part of the board here. The time-dependent, so partial t of the wave function for particles equals what? Yeah? Negative 8 bar squared over 2m. You'll write it so many times that it will be like writing 1, 2, 3, 4. Yes, because solving it for various systems is what we do in this course. So we wrote that down as the x squared psi of x plus v of x, and then psi. Okay, so that's the time-dependent Schrödinger equation, because you see, it's commented. And we can immediately write, because we solve it a lot, we did it last time, the time-independent is actually very much related to. So we leave psi to be just a function of x here, plus v of position x, and we have a beautiful equality here that gives us the energy of the system, which is what we want to emphasize. In other words, we can, in fact, this is what Schrödinger did for the hydrogen, for the single electron of the hydrogen atom, and got quantized energy levels, En. Yeah. It's En. That was really the birth of quantum mechanics, because the quantized energy levels he got fitted with experiment. You could get that the ground state is minus 13.6 electron volts. You could check it. It explained what was obtained experimentally. So today we push it further and say, well, actually, since it is birth of quantum mechanics, he did it in 3 dimensions. And if you don't mind, I can just write this in 3 dimensions. So partial t of psi of r, just we want to be accurate, equals negative h bar squared over 2m. Yeah. And instead of just the second derivative with respect to one-dimensional position, we are going to use this nice inverse triangle. What is it called? I'm sorry?
Is it the gradient?
Yes, when it has no square, it is the gradient operator. Then when it is squared, what is it?
Is that Laplacian?
Absolutely, the Laplacian. That's the essence of working together, so that I listen to you and we remind ourselves of stuff. Good job, thank you. So the Laplacian, yeah, which is the square of the gradient, and then we put our 3D wave function plus our general potential energy. Unfortunately, we keep calling it potential, and like Griffiths pointed out in the book, we are stuck with it. It's a potential energy, not just potential. So V of RT here, psi of RT equals E. I'm going to change this so that we have something a little bit symmetric. All right. Okay, so E of psi of RT. That's the energy, right? Oh, okay, so we are still on the time dependent. That means we have our equality already, so we were fine. That's the time dependent. Now we can write the time independent, which will simply be like this one here. Time independent, but in 3D. So everything here will just be R. Is that okay? Any question? Where are we heading? we are now going to claim next that this Schrödinger equation does for us what Newton's F equals ma does. What does, just to remind you, F equals ma can be written as dp dt, as you saw in the reading. The time derivative of momentum equals, the mass, u squared dt squared, position. And that itself can be written as a negative of the partial derivative of potential energy with respect to position. Let me stay with one dimension. Are we together? Am I too fast? So we got that. That's what Newtonian mechanics gives us, position as a function of time. And once we have our initial conditions, we can predict, we can tell where the Newtonian classical particle is going to be for all times. So, since the claim is that the Schrödinger equation does for us what Newton's F equals ma does for a classical particle, what is the equivalent of x as a function of t from the Schrödinger equation? That will be our, what is it?
The wave function.
The wave function. The wave function. So psi, let's make it general, is the wave function. It should give us the energy. It should give us the momentum. It should perhaps tell us the position of the particle once we know the initial condition. But remember, it is a wave function. So what is waving? Wave function for a particle? That already gives us the smell of something fishy, Wave function for a particle. Yeah, that's because the particle is behaving like a wave, which is why in the first place we needed a new form of theory to explain experiments where particles behave like waves and waves behave like particles, where photons have momenta as particles. So that's it. It was not always clear immediately at the beginning of quantum mechanics what the wave function signifies. When Schrödinger solved his equation in 1926, he used this wave function, an expression he found from solving his equation. He used the wave function to get the quantized energies of the hydrogen atom, but not much more. It was left for Max Born, so I'm going to do number 9 right there. It was left for Max Born to continue from where Schrödinger stopped in 1926. So number 9, Born then said, listen, Mr. Schrödinger, you have done very well to give us a wave function that is in general complex valued. So we can write psi star psi. We can take the complex conjugate of your wave function and get something like its modulus. When we square it, we get the amplitude, we get the probability. We get the probability density. So this is by Born. This, from your reading, the orthodox view, otherwise called what, please? Anybody? Orthodox view? The Copernican interpretation, which is the statistical interpretation, that the square of the wave function gives us the probability of finding the particle somewhere. So one probability density. Probability density. And to make that explicit, we can write it in a nice way and say the probability of finding the particle between positions A and B, between the integral, is binomial way of probability density, yeah, I'm using something you're familiar with, probability density, equals integral a to b of psi star psi, which is the same as this square. This is the wave function squared gives us the probability of finding the boundary sum. That's taking experimental results up to where we are. Any question? So now, if we solve psi and obtain psi for different systems, we can take the square of it and get the probability for that system, if it is an electron. So we're going to do a quick class exercise now to check this, and that's going to be on the PowerPoint. So if you don't mind, we switch to the PowerPoint. All right, after that, there will be time for break, and then we continue with other details. That was exactly 30 minutes, so that's good. I'm happy. We didn't take too much time on that. Okay, so we continue here. So you'll discuss with each other? Yeah. Let's get this back up. Okay. It went to sleep. So it's going to be a simple application of what we just landed with. Okay. All right. So we can do our connection. And where is our signal? Should be a wireless one. Okay, good. Good there. All right. So over to you. Class exercise. Discuss with each other and make your choice and convince yourself. Apply the statistical interpretation, please. Discuss with each other and pick your choice. See, we've got a wave function. Can you see? Time dependent or time independent? That's what you want to be sure. Yeah. So probability density. See? Do it on paper and see and convince yourself. Apply the statistical, bless you, apply the statistical interpretation. And then we go on a short break.
Yeah.
Well, that's for if there's an I, right?
Yeah, there's
Most of the time, you get deals with.
I think you just square it. I think it's D.
Are we ready to vote? Anybody made their choice? If you've made your choice, please show by a lift of the hand. Very good. So let's discuss. The probability density is just the square of psi. You've been given psi, so square it and pick. Does that make sense? Yeah. It looks obvious until we have a couple of these on an exam, and yeah. But we want to make sure that everybody gets the basic. So have you now made your choice? Good. How convinced is your choice? Good. How about you convince your neighbor about your choice? Discuss your choice.
I thought it was D because I wouldn't know how to get A, B, or C. Personally.
I have no idea what A, B, or C is, so I'm going with D.
Right. Always got
Where is the fun then?
which one do I
I don't know why it
recognize?
is.
Yeah.
Okay, so we now vote. Is that okay?
Mhm.
Those for A, B, C, D, E. Just to be sure. Awesome class. That's the statistical interpretation. Yes, please.
Why is it time independent if there's I know that there's no T inside of anything, but why is it x of T if it's time independent?
Why is what, please?
Why is the wave function x of T like it's the wave function of x comma T and then it says it's time independent?
Okay, so probability density at time t. So this is probability density at time t equals 0.
Oh, okay.
Aha!
Gotcha.
And this is the initial condition similar to Newtonian initial condition.
Okay.
Good question. More questions? So we're on. About 2 minutes break, and then we go into more details of the experiments and the theory on the slides. Is that okay?
If it was just C instead of 0, it would be 0, 1, 2, 3.
I did too, though, because I think same thing, this square counter, I was like, I don't know conjugate,
That's
the so I'm just gonna go on.
0 is just the number you just so it's only time independent
Oh,
because
I
we
see
have a
what you're
discrete value.
Because essentially, if you look over the like,
I guess if you had x of t, then t, there'd be another
that helped a
plus
lot,
of
like I
t
knew it
inside of it.
really well then, but I kinda forgot it.
I can hear that. That's correct. People are thinking nicely.
So much in classical mechanics
I
too.
know.
I was always
Where E or I would come from.
Well, you can write sines as cosines from Euler's formula.
Just E, I.
The I theta is equal to cosine theta plus I sine theta. So you can rewrite sines as cosines as e's, but so that's the only part that possibly. Yeah, but like
It's kind of
so you
funny.
just don't make
All of it
sines.
is like flooding back when you go through it. Like you just start remembering stuff. What is the gradient squared called again? I don't think I've ever seen that.
Yeah, so it's a Laplacian. The spelling is Laplace, so Laplacian. Yeah, so it will just be partial x squared plus partial squared partial y squared plus partial c squared. If you're using Cartesian coordinates. Yeah. And
Yeah.
it yields interesting results when you have to do that. You remember doing it in
Yeah.
modern. Yeah, it's now coming back.
I remember the gradient. I don't think we ever did we do something with the gradient squared?
I don't know if we ever used that name, we might use.
I think we did gradient squared, yeah, but I just don't.
Then I'm just not remembering.
Yeah,
We
that's,
didn't
remember
use
that.
that name.
yeah.
I don't know what it means, but I remember that being burned or image.
If you know the gradient, then the
Yeah.
gradient.
She just wrote out the
partial.
partial.
She wrote it to us.
Yeah.
Yeah,
They're really
she
cool
wrote out the
because
partial, and then you have
they lead to spherical harmonics, which we need to solve the hydrogen atom, for example, quantum mechanically. Yeah. Okay, people were asking very interesting questions. You are really on top of it. Can we continue then, please? Any more questions on this? All right. So, so
Okay.
details of the experiments. Those were just largely equations, and now we're going to the details so that you will always think of quantum mechanics as a theory that explains experiments and not some weird stuff. After we go deep into the theory. So, in the latter part of the 19th century, that means 1890, 1895, Physics was a mature science and armed with all this Newtonian mechanics, so Newton, Maxwell's equations for electromagnetic theory, Boltzmann statistics for statistical mechanics, and then special theory of relativity. Yeah, Einstein, 1905. And at a point, some people said, listen, there's no problem that we could not solve. It's done. We are done with physics. It's all over. Yeah. In fact, the famous physicist said that, unfortunately. His name is actually here. Let's not talk about it. He was dead wrong. Because then we started getting those experimental results that could not be explained by this theory. So but there were a number of seemingly unrelated problems that were proven particularly stubborn. For example, black body radiation. Yeah. Photoelectric effect couldn't be explained. And if you think it was easy to explain it, well, Einstein did it in 1905 and got the Nobel Prize for it. That tells you it wasn't easy. Yes, $1 million for explaining it. Then that's surely something not so easy to explain. That's what he got the Nobel Prize for. So that's the photoelectric effect.